All right. With that, hello everyone. Welcome back to Comp 2150 Object Orientation. Thank you all for waving back to me. I really like that. Thank you all for waving back to me. I appreciate that. Today we are going to talk about kind of a bunch of different things. I want to spend some time talking about types, subtypes, casting, and side effects of moving up and down in inheritance hierarchies, both in the context of on the stack, so stack-based allocation of objects, and also heap-based allocation of objects. So what's kind of happening there, and what kind of things can we consider as we are moving up and down in that hierarchy? This is going to be both kind of a visual, conceptual idea of what this looks like, and also a mechanical. I've got some code written that I want to show you to see approximately what's happening so we can sort of think about this idea. We're also going to talk about encapsulation today, and I know that this is something that you've talked about in 1020, and I have a little kind of review quiz from 1020 for that specifically. The focus of our discussion on encapsulation today is going to be from the perspective of design. So we probably have some rules that we've been blindly applying since Comp 1020, and I want to change the rules that you're using to decide which access modifiers you're picking for different parts of a class. Another topic that I'm really anxious to get to, I really want us to get to it today, that is related to encapsulation, is building on stuff with encapsulation. So actually starting to talk about something new that you don't know about yet, probably with encapsulation. It's not part of the learning outcomes for Comp 1020. And we're going to be talking about packages, so packages in Java. You might have used them before, you might have made your own, but it's not really formally part of your university program up until right now. So we'll spend some time talking about that today. Okay, so substitution. We spent a bunch of time talking about like these really weird ways to do inheritance. All of them, except that one that's called containment or composition or delegation, all of them are using that extends relationship, that hierarchical. Like we've got a supertype and we've got a bunch of subtypes beneath that supertype. We talked about this word substitution in the context of Liskov. So Liskov's substitution principle. The idea, again, with Liskov's substitution principle is we've got an interface that has been defined by a supertype. Our supertype defines an interface. It's kind of giving us a contract. It says, this is what calling methods on this object, instances of this object will do. Liskov's substitution principle is if you replace that specific variable with an instance of its subtype, it should still satisfy that contract that's been defined by the supertype. That's the goal of this thing. Substitution, though, it's not just Liskov's substitution principle. It's also something that we can think about in terms of code. We're not really going to be thinking about like how do you implement substitution. Again, this isn't a compiler's class. This is more about conceptually kind of what's going on underneath when we're applying substitution and when we're doing substitution with code. So we have something that we have learned about in this course called dynamic class binding. Dynamic class binding is, in code, effectively what we are trying to accomplish with this idea of substitution. When we've got a piece of code that looks a little bit like this, we've got a class that's a supertype and then a class that's a subtype. I can create instances of those types, and I can assign to a variable that has the static type of the supertype. So here on the third line of this piece of code, I've got A star, so a pointer to an object of type A is equal to a new instance of A. That seems normal. I've got B pointer to a type that is of type B. I'm assigning a new instance of that to itself. That's great. Substitution here is this line right here. A is equal to B. I have a static type on this variable called A that is pointer to A, but I can assign to that an instance of something that is its subtype. I'm allowed to do that. What I've done here is I have substituted the type of A with an instance of B. Instances of classes. So when we're thinking about instances of classes, and when we're thinking conceptually about what they look like, instances of classes that our programming language are creating for us have additional data about them. We don't talk about this. We don't talk about that. We don't talk about Bruno. That's immediately going through my head. We don't talk about Bruno, and now I can't stop thinking the song in my head. We don't talk about Bruno. We don't talk about the metadata that goes along with objects that get created by our programming language, but our programming language, C++, Java, these languages are themselves kind of going through this process of designing their own structures. A C++ compiler now is written in C++, but historically was written in C. A program that would read C++ code and then produce a program as output. When you call your constructor on an instance of your object, you've got class A and you've got class B, when you call that constructor, there's other stuff that's happening underneath what you're doing. One thing you might have noticed if you're using Valgrind for the last assignment, for assignment 2, is it says there's so many bytes free when I have one instance of something that I haven't reclaimed, but that number of bytes is mysteriously bigger than the number of bytes that are attached to the properties that I would expect to have. So I have 80 bytes missing for something that has 2 or 3 properties attached to it. Where is all that extra stuff coming from? Programming languages like C++ will have metadata attached to them. And that metadata in this case, when we're thinking about substitution, will be metadata that includes what type is this thing? What type is this object that I've got? Here I've got a code sample that's got 2 classes, so it's the same sort of idea. I've got a supertype, I've got a subtype, and then I've got some usage of those properties. I'd like to take a look at approximately what this might look like if we were to draw out memory physically. So I'm going to kind of scan through this. Is that okay at the back? Can you see that okay? Okay, good. Thank you. I've got these 2 classes, A and B. Conceptually, again, we're not bringing out the address space layout anymore. We're just thinking about approximately what these things look like. I've got these 2 objects that I've created. I have a variable called A. It has a static type of pointer to A. I've got a variable B. It has a static type of pointer to B. And I've assigned instances of each of these separate types to their respective variables. Underneath all this, what's happening is I have a variable, an instance of a variable here. This is a pointer. It has an address in it. The address that A refers to is somewhere in main memory. And what we have in the object, in the place in main memory where this object is some metadata about this thing. So when I called my constructor here, I got some extra stuff that includes metadata about this object. So new is allocating some memory, and it's stuffing some stuff in there that says, if I'm looking at this object at this location in memory, it has a type of A. Similarly with B, B is a subclass of A. It extends A, so it has the same properties as what A has, but it's got this additional one. So there's not much that's different about it. It extends it, it adds one more property, and we have this type of A, this metadata of A. This metadata may also include things like, this is assignable to the supertype. It has a supertype of this other supertype, so we can do assignments with it. When I make an assignment, between these two objects. So I am substituting an instance of this variable b into its corresponding variable a that has a super type, static type attached to it. Effectively, what I'm doing here is changing my pointer. Whoops, I need my pen. I'm changing my pointer of a star. And I'm just saying both of these variables refer to the same location in memory. Using these two variables, though, I'm only really able to interact with that object through the variable using the interface that's defined by the static type that's attached to that thing. So anytime I'm using this variable a, I can only do things like say, well, the static type of a has a property of x. So I can refer to this variable x. The static type of a has this property of y, so I can refer to this property of y. We're okay with that so far. We're good with that so far. But the interface that's defined by a doesn't have this the subtypes stuff in it. It doesn't know anything about z. So when we refer to this location in memory using this pointer, the value that we have that's attached to this object is kind of got this extra z variable obscured. It's still there. It's still there, but I can't refer to it from a itself. If I use b, this variable b, whoops. If I use this variable b, I can actually refer to z. That's okay, because the static type of b is of type pointer to b. So it knows, that type knows about all of those things. When I make this assignment, a is equal to b, I'm not changing that underlying memory. I am not changing that underlying memory. I'm not discarding anything. I just have two views of the same data now. One of them is I can see all of the properties that are part of the B class. One of them is I can only see the properties that are part of the A class. Make sense? We're good? Good, good. I can't go backwards, though. I can't go backwards. I'm not allowed to take this thing that is b. So b here, remember, is defined as pointer to b. Even though this object that is called a points at an instance of b, so it's got all the properties that b had, all that data is still there, I can't do this. I'm not allowed to do this. I can't do this because the static type of a is pointer to a, and the only thing that a has as a class is those two properties. If I were allowed to do that, the situation that we'd basically be in is, if I'm assigning something of type A to B, the value of z is, I don't know. We don't know, because when we're interacting with this variable here, this variable that is a that has static type pointer to a, we don't even know that that extra thing exists. We don't know that it exists. So for us to go backwards and say, okay, well, I know that this is an object of type B. It's fine. For us to go backwards, the only way that we can do that is to use that dynamic cast feature in C++. We have to use this to basically say, I know for pretty certain that the thing that this object refers to has not only enough memory to be interacted with as though it has that interface of what I'm casting it to, but if you convert it into this, you can have a fully populated copy of this thing. You're allowed to do that. Would B exist still? So yes. So what that's basically doing here, in the state that we're in right now, I'm going to put this. In the state that we're in right now, the pointer that is A is equal to the pointer that is B. They are equal to each other, right? They both point at the same thing. They're both pointing at the same thing. So in that sense, they're both pointing to this same area of memory. And now we're basically just trying to say, I want to copy this pointer, whatever we're pointing at with A. I'm trying to tell my compiler, yes, this is actually an object that has type B. This is an object that has type B. So Z always exists in that sense.
But with dynamic math, like, isn't it B that's getting turned into A? Or are you pretending that the previous line exists?
So yeah, I'm pretending that this is an iterative thing. So like we've done the assignment and they're equal to each other. So now we're trying to get that pointer back. Yeah, so it's basically not a great example, I guess, in the sense that I'm just assigning a value to itself again. But I'm trying to say, in order to do that, even though we know that that's the case, we have to tell our compiler that it's OK to make this conversion between those two types. Does that make sense? Yeah, so the dynamic cast, this function here is basically going to inspect the metadata of the thing that you've passed to it. And it's going to try to ask questions like, can I actually make this assignment? Is there something that is compatible with a pointer to type B in this memory location? And then if there is, you get a pointer. If there's not, you get that null pointer. Yeah. Good. Thank you for that question. That's great. We OK with this? This looks OK? Good. OK, good. In C++, so what we've just talked about in terms of dynamic allocation of objects, using our constructor, calling new and allocating new memory, this sort of applies to both Java and C++ equally. If you want to go backwards in the hierarchy in Java, you have to cast it in the same way that you have to use dynamic cast in C++. But the same general structure applies. An object in Java has some corresponding memory location that's being used, and it has metadata that's attached to it that includes things like the type. C++ gives us this ability to have stack allocated objects. So instead of always having to put new instances of a class on the heap, we're also able to put it into a stack frame and use memory that's in the stack to have that object. I've got a code example for this. So I've got this program that's called stack substitution. And it's got something that is effectively the same as the classes that we just saw on the slide. It's just got two classes where we've got a total of 3 properties. So A is the supertype. It has an integer. It has a string. And then B is the subtype, and it has a floating point called Z. I've declared a bunch of extra methods and constructors on these classes just to get it to compile, But the structure of these two objects is otherwise identical. So I'm going to go down here to my main function. In my main function, I've created stack allocated instances of these objects. And on line 51, what I'm doing is copying into the variable that is called A, the values that are in B. I'm going to run this, and I'm going to run it through my debugger, because I want to step through what's actually happening with this. So I'm going to do LLDB on stack substitution. I'm going to break on main. I'm going to run. And here we are. We're running. I'm going to step over these two constructor calls. I think they're straightforward. There's not really a lot that's going on here, so I'm just going to step over them. But now I'm going to step into what we're doing here. So stepping into this is calling my assignment operator on this type. But what I want you to note is that the assignment operator that's being called is taking a reference to a type A. It's taking a reference to the supertype. B here is of type B. A is of type A, but this assignment operator, the method that's actually being invoked, is taking a reference to type A. That kind of means a similar thing to what we just saw with dynamic allocation. In dynamic allocation, when we've got this pointer to A that's referring to something that's of type B, we're limited to the access that we have for the properties that are exposed by that object interface. When we're looking at an instance of type B with A's interface here, we're limited to the properties that A has access to. We're limited to the properties that A has access to. So all we can really do here is take the two properties that A knows about. And the only two properties that A knows about are X and Y. It cannot see Z. It has no idea that Z exists because the type A doesn't even know that B exists. It doesn't know that it's there. The other thing to remember about this specific situation, about assigning an instance of one object to another and using this assignment operator, is no new memory is being allocated. No new memory is being allocated for this object. So the difference, remember, between copy constructor and assignment operator is that copy constructor allocates new memory. Assignment operator just reuses the memory that was already there. So when I make this assignment, the variable for A, it only has enough memory for an instance of A. It only has enough memory for an instance of A. We can't just jam an instance of B in there, even though they are compatible hierarchically. So that kind of means that it's not that the variable or the value for Z is obscured now. It's literally just gone. It's not there anymore. When I make this assignment, I'm copying the properties from B into A, but I'm not copying that extra parameter that I just don't know anything about in my assignment operator. So as I step through this, I can print out what A is. Summary string parsing error. Okay, well, it doesn't want to copy my my string properly, but I get X out of that. But it doesn't know anything about Z, and it can't know anything about Z. The big difference is that copy constructor, again, dynamic memory allocation, we're allocating memory for this object. With stack allocation and the assignment operator, we're not allocating any new memory. You okay with that? You okay with that? Okay. Switch back here for a second. Going backwards in this situation doesn't make any sense. If I try to do, so let me quit my LLDB here. Let me quit my debugger. If I uncomment this line right here, so just go backwards. I just copied B into A. So if I do B equals A, based on what we saw before with this dynamic memory allocation, that would in theory be okay. But because we're doing all this stuff on the stack where we've got these fixed sizes, we can't go backwards. There's no dynamic cast here anymore. We can't go backwards from here. Let's try to make this. To assign from a class A into a class B, we haven't defined an assignment operator. This isn't telling us really that we can't do it, that we can't cast this other type into another instance of its subtype, but it's telling us there was no assignment operator for us to be able to do this in the first place. So let's add one. Let's really quickly add one and just think about it for a second. I'm going to add to B an assignment operator from type A. So an assignment operator from type A would look like this. It's the same as the assignment operator from type B. It's just got an A in it, a reference to an object A. I'm going to copy my assignment operator here of type B. I'm going to say A, whoops, uppercase A. And there's one line here that's a bit of a problem. A doesn't have Z. There is no Z on A. If I try to do this, we're also going to get compile time error. There is no Z in A. So the thing that we would try to do here is basically, I don't know. I don't know what that's supposed to be. I can't copy from the supertype A because properties that are supposed to be in this class just don't exist in that supertype. So we can go like forwards and backwards with dynamically allocated memory because the memory that we're working with never really goes away. It never gets transferred into some other object. It doesn't do anything like that. The problem that we've got with this is that as we go from one to the other, we're losing information. That information is just lost. It's gone. With dynamic allocation, the memory that has that subtype still exists. The memory that has that extra property still exists, and it's still allowed to be used. But here, it's just gone. We've copied it away from something else, and it's not possible to get it back. Okay. Yeah. Yeah, so we could say something like this. That'll work. But from a design perspective, the question then becomes, what is the default value? What would you pick in this case? You might have a default value that's part of your null constructor. You might just copy that. That might be reasonable. But the conversion between B and A here is explicitly losing information. So if we do have this like variable swap sort of thing, we're just going to lose something in there. Yeah. Any other questions? You okay? Good. Okay. Okay, let's get the hell out of C++. Let's talk about something different. Yeah, we can all cheer about that. Let's talk about encapsulation. After you finish your homework of watching Adventure Time, which will take you a while, you can watch The Wizard of Oz. I think it's been public domain now, so you should just be able to watch it, I don't know, wherever you want. I think it's in public domain. Encapsulation, this is a definition that you've seen before, is restricting access to implementation details of a type. So we've got a class that we've defined. Encapsulation is basically saying, I'm going to hide details about the way that I work from the outside world so that the outside world doesn't know about how I work internally. In Comp 1020, this is the learning outcome that you should have been able to satisfy. Explain how and why the concept of encapsulation is useful and how encapsulation is achieved through access modifiers and accessors and mutators. And to that end, let's have a quick quiz on 1020 encapsulation, just to make sure that we're all on the same page about it. Not Alex. Let's curious. Devani and real Devani. Oh no. Master theorem. Is it a 2080? Yeah. Oh no. So I realized last class telling you about, oh, I used to program on these old Macintosh computers. I'm just like, I am dating myself. Now I'm going to continue to date myself by saying, I don't know what that means. What does it mean to be based? I'm not joking. What does it mean to be? Is it a bad thing? Okay, thank you. All right, I'm going to start this. The game pin will stay up there. Good, good. Okay, yeah, so public. Interface is specification. So that's what we were talking about last time with those forms of inheritance. An interface is a way to specify the behaviors that a class or an implementation should have. Final is a way to say you can't change this or you can't extend it. And then class, arguably, it's a keyword that is related to encapsulation because you can't have encapsulation without class. But the best answer here is public. Okay, good, good, great, excellent, yes. Any class anywhere, like within the confines of the code that we're working in right now, any class anywhere can call something that is marked public. Good. Drop tables and CG. These are reordered, so please don't just slam the one that was in the same place last time. I mean, if you're competing, you can just, if you're trying to compete, don't just slam the same one as the last time because they get switched up. Okay, good. So an inner class here, just to be clear, an inner class is a class that's defined within the scope of another class. So like you've got public class and curly braces, and then inside those braces, you have another class definition. This is the best answer here, subclasses. So something that extends something else can access protected properties of its superclass. All right. Again, they're reordered, so please look for the correct one. Good. Okay, so no other classes can use something that's marked as private. Nobody, not even extension relationships, we're not allowed to access it. It's just entirely localized within the scope of that object. Good. Great. Great. Good. So yes, to hide implementation details is correct, but I'm going to argue that it's actually not hiding implementation details in and of itself. It's kind of exposing implementation details because you're basically saying, I've got all these internal properties that I've marked as private. Here are some accessors and mutators for you to access them and mutate them. This picture is what shows up when I searched for mutate. Viruses do not shape themselves as triangles. They don't shape themselves as triangles. They're usually more of a spherical shape, but they do have like protrusions sticking out of them. Well, that's really off topic. Okay, here's the last question. Okay, so the person that answered green is the C programmer in the room. The implementation details of a class are hidden. That's the definition of encapsulation. That doesn't mean that it's useful because that's happening. That's just the definition of what that word means. The two best answers here are to prevent unexpected modifications to internal state. Your object has a bunch of internal state that are the private properties. Encapsulating them, making them private so other classes cannot change them, prevents unexpected changes to those properties. To reduce coupling, to make sure that classes that are using your class aren't expecting your internal state to be defined in that specific way forevermore. It gives you the ability to make changes to the code that you've got without having to change the code that depends upon it. Way to go, drop tables. Little Bobby tables. Good job. All right, every question was answered correctly by most players. You all passed Comp 1020. Good job. Great. Okay. From Comp 1020, you were probably told some specific rules about what to do with using the keywords public and private. At first, you were told, you've got these classes. Please just put public on all methods. No exceptions. No problem. You were also then told, again, I'm guessing. I don't know who your instructor was for 1020. John Braco? Rob? Andrea? Who did you have for 1020? You don't know? That doesn't make me feel good about the state going forward of, okay. All right. You were probably told, at least initially, use private on data members. Always use private on data members. And then, no, hold on a second. There's extension and subclasses. So let's just make everything protected inside that superclass. Things that are outside of my hierarchy can't get into my hierarchy's internal implementation details. So just make it protected and then allow my subclasses to make changes to state inside of me. No problem. It's a lot easier than writing all those accessors and mutators. When you made this switch from let's just have everything be private to let's have everything be protected, and we've accomplished the same thing. We have accomplished the same thing. Something that's extending me kind of has to know about my implementation details. That's something we looked at sort of with C++ in the sense that in order to extend a class, you have to include that header. You have to include that header. You can't just forward declare it. If we're just going to make all of our variables protected so that our subclasses can have access to them, then why bother with private at all? Why have private? Why even have a private access modifier in the first place? Just blanket replace it with protected. The goal of this private modifier is to prevent external modification or of access to internal implementation details from the outside. Who even is external here? You and you and you and you and you, you're all writing your own subclasses. Why would I mark something private if I know that I'm not going to make a mistake? If I know I'm not going to make a mistake? You're not going to make mistakes, right? Right, okay. And I mean, that in and of itself is kind of a justification, but more realistically, in this course, we need to start thinking about designing code for other people, In most university courses, you're kind of in the state of just like, I write code for me. I mean, you're submitting it to somebody, but the code that you're writing is really only read by you. It's only ever used by you. And some people are like terrified of showing code to other people because they don't want misconduct situations to come up. Yeah, of course it's just you when you're thinking about university courses. But as you're growing as programmers and developers and computer scientists, in the real world, you are working on a team of people that have a shared code base like all together, not just you working on stuff for yourself. You have a big project that has 10 or more developers all working on it collectively. There are other people that are going to be using your code. There are other people that don't know about what your internal state is supposed to be. There are other people that are starting to work with the code that you're using. Other people who are not you. I want to really emphasize that. Other people are not you. Other people are not you. It's really hard. So I'm sorry for hearing you at the back, but you say it's 3020 again. Yeah. Yes, this is 3020 again. And for those of you who have not yet taken 3020, 3020 is HCI, human-computer interaction. And one of the things that you learn about in HCI is you are building software that has an interface, like a touchscreen or whatever, that is not for you. You are not building that thing for you. You are building it for other people. This is the same idea. You are building code for other people who are not you. Access modifiers are a way that we are defining interfaces for the class. So yeah, man, you picked it up. You just said HCI, and I'm just like, I'm going to jump on that. When you're designing interfaces, like you've got a touch screen here, and I've got buttons that I can push. You're designing an interface that we can see as a user. But we can talk about this same thing in terms of code. Access modifiers are tools that you can use as a developer to design the interface of your object. That's what we're really doing. We're not just hiding things from external access. We're designing the interface for the code that's going to use our code. There's two ways that the interface of our class can be used. One is other unrelated classes that are calling methods and using properties of our class. This is the way that we kind of started with coding. We defined classes, and then we used those classes in other classes. We created new instances of them. We called methods on them. The way that we're defining the interface of our class in this sense is by using the public keyword. Anything that's public can be used by classes outside of us. The other place that the interface of your class is used is by subclasses of your class. We don't normally think about it that way. We think of this hierarchical inheritance relationship as like, this is the way that these classes are related to each other. But really, a subclass of a class is using the interface that's defined by its superclass. That's what it's doing. It gets that interface, but there's also an interface for it to interact with the internal details of that superclass. Here's an example of some code. This is in C++, but it's kind of like the style of code that you might have written in Comp 1020. If you have written this code that's class A, and it has this internal property that's called x, and you said in a comment, this value should never go below 0. You wrote that comment to yourself, and then I got your project, and I wanted to start using the classes that you've defined. I wanted to start using your interface that you have created by creating this supertype that is A. You marked this internal property x as protected. You marked it as protected, and that means that I have access to it. That is part of the interface that you have exposed to me as a superclass. And I can just write code that violates the assumptions that you made about the internal state of your class. I can just come along and make my own method and just start making changes to the state that you have defined as the superclass. Protected, another way that you can think about protected is kind of like public for subclasses. It's part of your interface. This extension relationship has an interface between these two classes, and marking things as protected effectively makes them public for consumption in the subclass. A better way to approach this would be to keep that internal state private. You can continue to write this comment up here that says x should never be less than 0. And then you can hide the implementation of x from me as a subclass. You can hide that from me as a subclass. And you can provide public methods to me as a subclass using this protected keyword that are mutators for that type. But because you are controlling this public to subclasses interface, you can enforce the behavior that you've stated that's part of the interface that you've got. This is a lot more code. I agree, it's a lot more code. And it's a little bit more painful in the sense that you have to provide this external access through a method. But in terms of designing interfaces for code to use in this inheritance hierarchy, this is kind of what I'm expecting you to start doing. So this is C++, but I'm expecting you to start doing stuff like this in Java as well. As opposed to just blindly making internal properties of a superclass protected, start to make them private and provide protected access and mutation to those properties in the superclass. Is that okay with everybody? You're good. Okay, good, good. Oh, thank you for bringing that back. I have lots more in case you want one. Seriously, I don't want to chuck all these out, so I'm just going to carry them around with me. Every class you write has some kind of ownership over stuff. The ownership that every class you write has is over its own internal data members. So every class, every instance of a class that you have has state. Every class that you write, the definition of the class, has ownership of that state. The responsibility here now is that we've moved this ability for external classes to just blindly change the state to it's the responsibility of the enclosing class itself to make sure that the state remains valid. I said as a superclass, this is the way that you should work with my code. This value should never break this assumption. This is really kind of tightly tied with the idea of design by contract that you saw in Comp 2160, that you should have seen in Comp 2160. Okay. Just in case you didn't, or just in case it's been a really long time since you took Comp 2160, the three key parts of design by contract here are preconditions, postconditions, and invariants. In the example that I was just showing here, this dec function, this dec method that has been marked as protected has a precondition. The precondition here is effectively saying, I'm not going to make changes to this if it's going to make my value below 0. The post condition here, while unstated, is you can assume that after this method has run, this value will not be below 0. This is also enforcing an invariant in the sense that it will never get below 0. We're never going to allow this thing to get below 0. Taking this idea of design by contract and then putting that into what you have for mutators is kind of the idea that we're going for here. And exposing this interface to subclasses and enforcing that behavior and keeping that ownership and validity checking local to the class that owns that thing is what we're trying to get across. The accessors and mutators that you definitely wrote before are just blindly accepting things. Yeah, that looks good. I'm going to just copy this value. This dot x equals x and like finished, right? As you're going forward now, what I want you to do is to start taking this idea and applying design by contract to your accessors. You may want to do things like saying invariant checking on, I'm sorry, I want to restate that. You may want to do things like having invariant checking on accessors. The mutators are the ones that should have preconditions. So making sure that you're rejecting things that don't actually satisfy the constraints of what you've got for your internal state. So this is basically saying the same thing here. Taking that idea that we've got as mutators just accepting blindly whatever it is that we want, starting to enforce preconditions and design by contract into the mutators that we have, and then limiting the access to subclasses for that thing. Okay, so I think you have a reasonable idea of what this looks like, but the rules have changed since you were working with objects in Comp 1020. So I want to just quickly step through this. For public instance variables, basically never. Your instance variables should basically never be public. That's kind of a non-option, and it's been a non-option for a long time. Public methods, if another class that's outside of your hierarchy actually needs to access this thing, or it actually needs access to this behavior, then yes. If you can enforce assumptions in that method, then yes, use public for the methods that you're defining on an object. Protected instance variables, basically never now. You shouldn't have protected on instance variables anymore. Methods, if a subclass needs to be able to make changes to the state in its superclass, it should be done through a protected method. If you haven't otherwise marked a mutator as public, then it should be protected and not public. Again, you kind of have the responsibility of enforcing the assumptions that you have about the internal state of your object in this mutator that you're writing right now. Private instance variables, just blindly always yes now, yes. And I mean, I think that was mostly true before, but now it's always yes, always yes. Methods, sure, if you want to have a private method and it makes sense to have a private method. Public should not be the default option for methods unless it's something that you actually need outside this class. If it's not something you need outside this class, then private is a good default for a method, unless you need it for sure in the hierarchy of classes that you've got. Good, yes, good. Lumpy Space Princess, yeah, okay. Let's do something different. Let's talk about packages. Java packages is a feature of Java that you have used extensively. You have used this extensively. You have made use of packages. You've just never really defined your own before. Java packages are effectively a physical and logical organization of classes. It's a way for us to start organizing classes on our file system, but also logically grouping related things together. Java packages have additional access modifiers on top of public, private, and protected. And we're going to get to that a little bit later, but it's a preview of what's coming. Something a little bit maybe unexpected based on what you've seen before. Java packages are effectively a way to physically organize and logically organize classes that are related to each other into groups that's not a hierarchical relationship. It's not a hierarchical relationship in terms of inheritance. You've used packages extensively before. I know for certain that in Comp 1020 you wrote that first line probably a bunch of times. Maybe you didn't write it and you just got VS Code or whatever to write it for you, but it's something that appears in your code semi-frequently as you're working through problems in Comp 1020. Did you use swing in Comp 1020? No. What did you do? Did you do any GUI stuff in 1020? Did you do any GUI stuff in Comp 1020? Oh, but you didn't use like J option pane. Oh. I use J option pane, but I'm an old person. I've quickly learned teaching the last two classes. I use J option pane, and to use J option pane, we have to import the swing libraries from Java. Okay, I've digressed. Java's standard library, the whole thing is organized into packages. This is a link that you this is a link that you have probably seen before a bunch of times, but all of the classes that are provided by the Java standard library have a package. It's usually java.something.something. Java, as recent as Java 9, I think we're on Java 19 now, Java also has this idea of something called a module. We're not going to talk about modules in this course. Modules are related to compiling Java code into smaller packages as opposed to delivering an entire JDK. All we're going to care about right now is packages themselves. So a way to logically organize and physically organize files and classes. That's what I'm looking for. Let's start by making our own package. Making our own package it's straightforward. It's actually really, really straightforward. Creating and using our own packages is a combination of a folder structure, so like making folders on our file system, using the package keyword in the classes that we want to be inside of a package, and using the import keyword to get access to the classes that are inside of some other package that's not the folder that we're currently in right now. Let's make a quick package here for shapes. So I'm going to switch over to VS Code. I'm going to say goodbye to stack substitution.cpp. And I'm going to open up specialization.java, sorry. This is that program that we used last time to demonstrate this idea of specialization and then replacing subtypes using an interface as the type of the variable, so doing substitution with interfaces. I want to kind of go through the mechanical process of what you would do to create a new package and then create a new class in that package and then use that class. The first step is to make a folder. You can make a new folder in Visual Studio Code. You can make a new folder in your File Explorer. You can make a new folder on the command line. I'm going to make it so that it's the right, I can't even type. I'm going to make it so that it's the right name. I've made a folder. Step 1, complete. I've done it. I'm going to go into this shapes directory, and I'm going to make a new file in here called circle.java. VS Code has done this for me, but because this class is now in this folder that's called shapes, I have to have the keyword package at the very top and then the name of the folder that it's in. So shapes here. I'm going to run a program on my command line. I'm going to say make clean first. And then I'm going to run a program that's called tree. Tree is just like printing out the folder structure that we have from this directory right now. So I've got specialization.java. That was the first program that I opened. I've got a folder called shapes, and I've got a file here that's called circle.java. I'm not going to do anything in Circle right now. All I really want to do is create a new instance of this type in my other program. So in specialization itself, the very first thing that I have to do is import this class. Because the file isn't in the same directory that I'm in right now, I have to tell Java where to find the class. So the way that I do that is I say import, and then the name of the directory, so shapes, and then the name of the class that's beneath that. Or I can use an asterisk to say import everything that's in this directory. I'm going to say circle specifically, similar to my rationale for saying I want to include string in C++ explicitly rather than getting it by transitivity through IOStream. I want to include just the name or import just the name of the class that I want to use rather than importing everything into my class. This is a just me thing, but what I'll write here is import shapes.star is effectively the same thing. And now we can make a new circle. Circle isn't related to the types that we have in this class. So I'm going to say circle C is equal to new circle. And that's it. That's it. We're done. Great. We have created a new package. We've put a new class into it. We've imported that class into the class that we're working in right now, and we've used it. To make this now, to build this example, I'm going to run Java C specialization.java. And this is really small, but I'm going to run tree here so it's bigger. When I compiled specialization.java, it also transitively compiles this circle for me. It goes into that package and it compiles the classes necessary for that one. So I don't have to add any special processes to compile these dependent subtypes. The compiler is just doing it for me on my behalf. So I don't have to do anything special for that. So now we've gone through the mechanical process of let's build a package, we'll use a package. Now I want to start thinking about design again. Coming up with names for packages is basically just coming up with themes that describe the relationship between these files that you're putting inside the package. Again, they're not necessarily related through inheritance. They might just be several different kinds of subtypes that are otherwise unrelated to each other, but they have a common theme. So here is an example with something that you are familiar with now. If I have this idea of simulating stuff, I might have a few different packages that are attached to this. The simulator package might be for putting a main class in, something that's going to drive this whole thing. I might have an events subpackage, and this is just a folder that is simulator, and then another subfolder that's events, and then files within that. Simulator.events might be for classes that are of type event that I've defined in this thing. Simulator.io might be for all I/O related stuff. You might have several ways to do I/O in your simulator that are otherwise unrelated to each other, but have a common theme of being input and output that's for a simulation itself. Maybe you've defined some abstract data types, and you've got a queue that is implemented in your program. So you've got an ADTs and then a queue subpackage. And then you've got a package that's called I/O that's just for generic input and output stuff. Naming things is one of those hard problems in computer science. There's a joke. There's a joke. There's always a joke. There are two hard problems in computer science. Naming things, caching, which is something you've maybe seen a little in 2160, but is something you'll see later, and off by one errors. Okay, good. Yes, thank you. There are some like chuckles. The idea here is, again, just a common theme that kind of groups these things together. So not so much a hierarchical relationship with interfaces and inheritance, but just some common theme. Access modifiers in this new paradigm that we're talking about change the meaning of some of the access modifiers that we have been using. Public still means the same thing. If you have a public thing inside your class, it's accessible to any other class anywhere. It doesn't matter what package it's in. It's just available for everyone to use. Private still means the same thing. Private means if it's private, I cannot access this. It's not part of my public interface. Nobody else anywhere else can use it. It's only visible to the enclosing class. Protected means visible to subclasses. That's still the same. And other classes in the same package that are not hierarchically related to this class. Let me show you an example. I've got this public class specialization. It's in this main folder here. I've got this other file here called circle. It's not in the same package as those other classes. We can agree on that? Are we good? It's not in the same package as those other classes. It's not hierarchically related to those other classes. Let's take a look down here at this class, quadrilateral. We said that quadrilateral is a sided shape, and I've changed this just a little bit so that it doesn't hard code 4 anymore, but instead as a protected integer that describes how many sides this thing has. I've got to do something slightly different here. I'm going to make a new file real quick. I really want us to see this. I'm just going to copy and paste this here. It's now a public class. Okay. I'm going to move this into the shapes class, into the shapes package, I'm sorry. Move it. Okay. Quadrilateral is in here. It's in the packages shapes. And instead of trying to kill myself to do this, I'm just going to stop doing this one. I'm going to do this. This is terrible. I've got public class circle. I'm going to say protected int sides is equal to 0. We've got 0 sides in a circle. Good, I think we can agree on that. I now have this class quadrilateral. I'm going to put a main method in here. I'm going to create an instance of circle because we're in the same package. And then I'm going to say circle.sides is equal to, I don't know, 1,000. That's a lot more than 1,000. Quadrilateral and circle are not hierarchically related to each other. But even though this is marked as protected, I can make changes to that variable provided that these classes are in the same package. Really, really quickly, there's also a fourth access modifier that we get with packages, and that is to have no package modifier at all. So if I have something like this, I put this quadrilateral type inside the shapes package, and I just declare properties. So I don't say public, private, or protected. This is what's called the package private modifier, the blank access modifier. This says that other classes that are in the same package as me can access sides, but if I declare subclasses of this type in other packages, so if I distributed this code to you as a class file compiled, you would be able to make a subclass of this type quadrilateral, but you wouldn't have access to that variable because it's package private if you declared a new class outside of this package. All right, you should be able to now describe substitution in code. You should now be able to explain and use the concept of information hiding, use access modifiers appropriately, use packages in a Java program, and define the term package private. Thank you all for letting me have a couple of extra minutes of your time, and I hope you have a great weekend. Goodbye, everybody.